Hello and welcome to Los Alamos National Laboratory's Math and Science Academy. In this thread, we'll be discussing Common Core Standard 5.NF.B.4, the second part of it, which involves understanding the multiplication of fractions through area models. We'll be finding the area of a rectangle that has fractional side lengths and then showing the procedure that allows us to see that this is the same as if we had multiplied the side lengths. The learning goals for this standard are to translate a mathematical task into a visual model and to be able to visualize and understand multiplying fractions by fractions. As for all of our examples, the learning goals of fluently using multiple strategies and communicating mathematical thinking with precision and accuracy are also involved. Here's our problem. Create a map of a garden on a grid that is composed of adjoining rectangles, some of which have fractional side lengths. Find the area of your garden. In the example that we'll use only one rectangle for the garden to illustrate the mathematical ideas behind multiplying these two fractions. In a more complex garden, students will need to understand adding different areas together and perhaps calculating side lengths of their garden. But in our case, we'll use a single rectangle, and the choice of 5, 6, and 2/3 brings up some other issues that we'll see in a minute. We're going to use an area model by representing the garden first as a rectangle that is 2/3 kilometers in one direction and 5, 6 kilometers in the other. I haven't yet drawn the grid, but the first thing to notice is that the side length is a part of some whole, and we need to have an idea of what that whole is. And so we'll draw a whole square kilometer around the garden to understand that 5/6 is 5/6 of 1 kilometer. Well, if this is 5/6 of a kilometer, then we're going to break this whole distance into 6 equal parts. And we have 5/6 of a kilometer as the distance here, 5 out of the 6 whole parts. In the other direction, we have 2/3 of a kilometer, so we need to break this square kilometer into 3 equal parts, and that would look like this. So here are 3 equal sections in this direction of the garden, and of the whole, and 2/3 of them are the garden. So when we look at this, if you look carefully, now we're looking for this area, this kind of green shaded area, and it has a certain number of equally sized pieces in it. And those equally sized pieces are the same as this one, and if you look at it, you'll see that there are going to be 1, 2, 3, 4, 5, one more over here, making 6 pieces in this direction, and 1, 2, 3, a third one here, 3 total pieces in this direction. So the total number of these pieces is 18 within the whole square kilometer. So these are 18ths, and we can break up the rest of it to show that these pieces are all equally sized, and there are 18 equal sized pieces in the square kilometer, so they're 1/18th of a square kilometer. So now the problem is reduced to simply counting these ones that represent the garden, and you can count them. There are 2, 4, 6, 8, 10. So there are 10/18ths of that square kilometer that represent the garden, and we have it that our area is 10/18ths square kilometers. I am pointing out here that we should emphasize the units. This is a good time to introduce or reiterate that when you multiply kilometers times kilometers, you get square kilometers, and that the units of area are squared length, while the units of distance are a single length. Now, of course, there's another way to do this. We can see that this fraction 10/18 can be reduced, and if you look at the area model, you'll see that each pair of 18ths can be combined together, and we can look at this using ninths. You see that one of these squares is a ninth, and these are ninths, and we can count this same green area as in ninths instead of it in 18ths. And that's true because these two 18ths here add up to 1/9. And so we have 1, 2, 3, 4, and a fifth. These two together make your fifth ninth. And so instead of looking at it in 18ths, we can look at it as ninths. And we have that the area is, again, 5/9. In the standard, the student is asked to show that the calculation of area using unit fractions is the same as multiplying the two fractions. We saw in the previous slide that calculating the area by unit fractions was given by 5/9 or 10/18. In this slide, we'll show how to do the multiplication using a procedure. So again, we're creating a map of a garden on a grid using adjoining rectangles, some with fractional side lengths, and finding the area. The garden that we chose was a simple rectangle with side lengths 5/6 and 2/3, and we're going to show how to do that with a procedure and confirm that we get the same answer that we got before. So one of the fundamental ideas in finding areas of rectangles is that the area of the rectangle is the length times the width. This goes back to the fundamental idea of multiply. It doesn't matter which one is the length of the width, but we have our two numbers, 5/6 and 2/3. So what we need to do mathematically is do this multiply, 5/6 and 2/3. From work with area models and other visual tools, students should understand, hopefully by now, before they're doing this as a procedure, they should understand why multiplying fractions ends up being multiplying numerators and denominators. So that's the procedure. Multiply the numerators, multiply the denominators, and also multiply the units when we're working with ideas that involve units. So what we need to do is 5/6 kilometers times 2/3 kilometers. We'll multiply the numerators. 5 times 2 gives me 10. Multiply the denominators. 6 times 3 gives me 18. And my units also multiply. Kilometers times kilometers is kilometers squared. And these are units of area, while these are units of length. We know that we always want to reduce the fractions to the lowest terms. What lowest terms means from an area model is what we did earlier, is breaking the unit fractions into the largest possible pieces. So our 18ths, we were able to break those into ninths and still represent the area of the garden using a whole number of ninths. So that's reducing to lowest terms. And from a procedural point of view, we're looking for common factors. And we found a common factor of 2. 2 goes into 10, 2 goes into 18. So we can think of this 10/18 as 2 times 5 over 2 times 9. But the 2's will cancel out, and we basically have one fraction that's equivalent to 5/9. So our result can equivalently be written as 5/9 square kilometers. Another way to work with fractions, and some of you may have seen this, and as the procedure gets more sophisticated, you might want to introduce this to students as early as possible, is before you do this multiply, to do what's called cross-canceling. So some teachers use this, and students, once they get to be very proficient with the procedure, it's very helpful. So we start with 5/6 times 2/3, and student needs to notice that there is a common factor of 2 here and here. And since we're going to be multiplying them anyway, it makes sense and is convenient to cancel those common factors, that common factor of 2, before we multiply, so that we have smaller numbers and that we don't have to reduce at the end, which we had to do here. So that we do that by noticing that 2 goes into 2 once, 2 goes into 6 3 times, and we're essentially changing the 6 to a 3 and the 2 to a 1. And now, when we multiply straight across, we get 5 times 1 and 3 times 3, which is 5/9 square kilometers, and we get our reduced fraction without having to reduce it at the end. Again, this is a much more sophisticated way of looking at it and should only be introduced once the student fully understands the procedure and the idea behind multiplying straight across, and really deeply understands the idea of reducing fractions to lowest terms by finding common factors. So here's some teacher work on this problem. You can see they've rewritten the problem, and then they've drawn their garden on a grid, and the units that they've used are that 4 of these bold squares on the grid paper represent 1 unit. So they've got a rectangle that's 1.5 by 1.5 units. Actually, it's a square as part of their garden. And then another part is 1/2 unit here by 1.5. It's another part. And the third rectangle is 2 units this way and 1/2 unit this way. It's not entirely clear what the teacher intended in terms of breaking these up, but that's one way to look at it. Once they've drawn the garden, which is clearly a little bit more sophisticated than the one we did, now calculating the area becomes a matter of counting up square units. In this case, because each individual unit is broken into 4 parts, it's tempting to look at this from the point of view of sixteenths, because each one of these squares in here represents 1/16th of a unit. So when we combine together 16 of them, we get 1 square unit. And you see the teacher gets 1 square unit here from those 16 sixteenths. Another square unit here. That's 16 more of those sixteenths. And then here we have 1, 2, 3, 4, 5, 6, 7, 8 times 2 gives me another region that's worth 16 sixteenths. So this is a third whole square unit. And finally, we have another 8 sixteenths times 2, or another 16 sixteenths, which is a fourth square unit. So our area, total area, is 4, as you can see from the area model. When the teacher reinforces this through the multiplication algorithm, we look at, she's taking 1.5 times 2, which represents this 1.5 times this 2 units, gives me this rectangle. The area of this rectangle is 1.5 times 2, which is 3. You can kind of see it there. And those are represented by these 3 sets of 16 in here. And the other part then, which needs to be added, is this 2 times 1/2, which is 1. So there's another whole square unit, and the answer is 4. So there it is as a procedure in 2 parts. We could have, instead of looking at this as sixteenths, we could have broken it into pieces like fourths, depending on the grid paper. In this case, the units that were used are just halves, 1.5 and halves down here. So because the fractions lend themselves nicely to halves, we could have just broken this into groups of 4 and counted groups of 4. We could even have broken it into groups of a half of a unit and worked with it that way, had we so chosen, by breaking it up this way. And it just depends on how you want to look at the problem. So there are a number of ways to do that for this particular set of numbers that were used. It's a very good example of an image that's illustrating a concept and lots of different ways to think about it. And here's the procedure up here to kind of solidify that, in fact, the answer is the same thing. Finally, here's some mathematical writing that we might expect from a student on this problem. They've chosen a simple rectangular garden of dimensions 2/3 and 4/5, excuse me. And what they're identifying in the writing here is that 3 parts in one direction and 5 in the other gives us 15 equal parts in the whole. So here's a whole unit of whatever dimensions we're talking about, and when we have to break it into 3 parts one way and 5 parts the other way, we're going to get parts, each of which is a 15th. So the units that we're going to work with, the subunits, are 15ths. So, and they identify that here. The denominators define the units. Now these are the unit fractions that they're talking about, the 15ths. And then they're just going to do a multiply. The garden has 2 times 4 because there are 2 in this direction and 4 in this direction. Now we're looking at the numerators. 2 times 4 gives me 8 of these little subunits. And those units, again, since they're 15ths, the multiply gives us 8 15ths. So this is another way to look at it and understand the problem from a point of view of breaking it into individual units based on the denominator and then counting the number of those based on the numerator.